In this mini lecture, we are going to introduce the idea of inductance and inductors. We're going to talk about inductors, self-EMF, and inductors in a direct current circuit. When we have a circuit, and let's say we have constructed a circuit, we've got some elements in there, and we have a switch. When the switch is open, of course, we don't have any current flowing through the circuit. But when we close the switch, the current does not immediately change from 0 to the maximum value. There's got to be some initial rate of change of the current. And because of this rate of change of current, there will be a change in magnetic flux. And this induces an EMF, an electromotive force. So, we talked about how when you have current running through a wire, you can create a magnetic field around that wire, okay? But if there's some initial rate of change of the current through that wire, you're going to get a change of magnetic flux created by the magnetic field produced by that wire. For that same reason, whenever you open a switch in a circuit, the current doesn't immediately jump from the maximum value to 0. There's some rate of change of the current as that current is diminishing to 0. So this induces something that we call self-inductance. A changing magnetic flux through a circuit arises from the circuit itself. So you can induce an EMF in any circuit if you have a rate of change of current. And so that EMF, that electromotive force, is equal to minus the inductance of the device. L here represents the inductance of a device, times the change in current over the change in time. Now, we're going to be talking more specifically about elements called inductors. Inductors are coils of wire that you wrap around the coil of wire many, many, many times, and you create something called a solenoid, or you have a few coils of wire. Those coiled elements have an inductance associated with them. Those are the things that tend to contribute the most to the self-induced EMF that is created whenever you turn on a circuit or turn off a circuit. The self-induced EMF of a solenoid or of an inductor is this equation right here. That's equal to minus L, which is the inductance of your inductor, times the change in current over the change in time. So our inductance is a physical property of the inductor, just like how the capacitance is a physical property of the capacitor. So inductors and capacitors are somewhat similar. A capacitor stores energy in its electric field, and we talked about that in previous sections, but an inductor stores energy in its magnetic field. Here's how you can calculate the inductance, L, of an inductor. So mu naught here is the permeability of free space, 4 pi times 10 to the minus 7 Tesla meter over ampere. N is the number of times you wrap that coil around itself when we square it. A is the cross-sectional area of the solenoid. So usually a solenoid is kind of like a long cylindrical coil of wire. And so if you turn that solenoid to face you and you can see that cross-sectional area down the middle, that is the cross-sectional area of your solenoid. That's this here. So usually, typically that's a circle, pi r squared. And then you divide it by the length of your solenoid. The SI unit, the standard unit of inductance, is called the Henry, which we abbreviate as a capital H. With a capacitor, you get a separation of charge on the plates of our capacitor. So one plate gets all the positive charge and one plate gets all the negative charge. That creates an electric field inside the capacitor, and the capacitor stores energy in this electric field. Remember, the energy stored in a capacitor is 1/2 times the capacitance of the capacitor times the potential difference across the capacitor plates squared. Now, inductors store energy in a magnetic field. For an inductor, the energy stored in an inductor is 1/2 times the inductance of the inductor times I squared, where I is the current running through the circuit or the current running through the inductor. All right, so you can see that there's similarities between the energy stored in the electric field in a capacitor and the energy stored in the magnetic field in an inductor. So in our capacitor, we care about, for the energy stored, the capacitance of the capacitor. Those are their physical properties. And we care about the potential difference across the plates. And then for our inductor, for the energy stored in that magnetic field, we care about the physical properties of the inductor, which are the inductance, and then the current running through it instead of the potential across it. Previously, we talked about how capacitors behave in a direct current resistor capacitor circuit. So I called those DC RC circuits. Now we're going to talk about direct current resistor inductor circuits, DC RL circuits. You know you have a direct current circuit if you're using a battery. Batteries supply a constant voltage. Okay, that voltage does not fluctuate in time. Okay, so that is a direct current circuit. When we have an alternating current circuit, when our voltage source does oscillate in time, which also causes the current to oscillate in time, then we have an alternating current circuit. So here we're thinking about what happens when you take a battery and an inductor and a resistor and put them together in series. All right, so this is what we have here. We've got a battery, and then if we have this switch here closed, we've got a resistor and an inductor. In circuits, when we talk about inductors, or when we draw out the diagram, remember that our resistor is a, let's get this here. Our resistor is this zigzag shape symbol. Our inductor are these 3 humps here, symbol, kind of representing the coils of wire wrapped around themselves. So when you have a circuit like this, we've got a battery, resistor, inductor, supplied with voltage from a DC source. The current in our circuit cannot be turned off or on instantaneously. So we mentioned that a little bit previously, but the inductor in particular in the circuit can moderate the rate at which the current increases in the circuit or the current decreases in the circuit. So the current increases or decreases in a similar way as the voltage across the capacitor changes in a resistor capacitor circuit. Now these equations are going to look very familiar to you up here. These graphs that I have here show what happens to the current through the inductor once I close the switch. Okay. The current through the inductor starts out as 0, and then it increases like this. It takes on this increasing shape here. And the equation that describes how this current increases in the inductor is given by this equation here. I, the current at some time t, is equal to the maximum current you could achieve times 1 minus e to the minus t over tau. This is also similar to how the voltage changed across the capacitor whenever we had a resistor capacitor circuit. But instead of current, this was voltage. Okay. Now we see here that on the horizontal axis, we've got our time scale. On the vertical axis, we have our current. On the horizontal axis, the time is marked in units of tau, a characteristic time scale. For our capacitor circuit, that characteristic time scale was the resistance times the capacitance. For our inductor resistor circuit, the characteristic time scale is the inductance of the inductor divided by the resistance of the resistor. We see that at our characteristic time constant tau, our current reaches 63.2% of its maximum value, or 0.632 of its maximum value. If we let the circuit go for long enough time, many time constants tau, we'll eventually achieve maximum current in the circuit. Whenever we have maximum current achieved in the circuit and we're ready to open the switch, whenever you open the switch and you, let's say you open the switch over here in my diagram and connect it up here where it says 2, so that now in the circuit, all that we have is the inductor and the resistor. Our inductor was storing energy in that magnetic field. Now, whenever we close this switch here, a current is immediately going to flow through the circuit. But that current is going to diminish over time. And this chart here shows how that current decreases in time. And that is equal to, the current at some time is equal to the maximum current that you had to start with times e to the minus t over tau. And we, again, at our characteristic time constant, when that current is decreasing and we're taking the energy stored in that inductor and letting it go to create the current through the circuit, if we've disconnected the circuit from our power source here, then we reach 36.8% of our maximum current, or 0.368 of our maximum current at the characteristic time constant. So there are a lot of similarities here, what's going on with our RL circuit as compared to what was going on with our RC circuit.